Okay, we are now going towards the end of our seminar. Unfortunately, it's very nice. It's been a very nice seminar. I would like to say hello to my friends who are watching us online. Carla Gonzaga from Paraná, and also Larissa Cavalcante in Rio, and also Rodrigo Otávio in Rio Grande do Norte. Thank you very much for your audience. And Marcos Schroeder from Rio too is watching us. Thank you very much. You can keep sending your questions to my email or to my phone via text message. Okay. Our next presenter is Jason Griggs from the University of Mississippi. Thank you, Jason.
So how is the sound level now? Is everybody okay back there? Sometimes when I have a big room, I get excited and speak too loudly. So Dr. Lobauer would have to kick me if I start to get too loud in the middle of the presentation and I don't notice. All right. So I want to thank you for allowing me to come and talk to you. It's very gratifying to see so many people here who are interested in dental materials research. Very positive. And tell you a little bit about where I'm coming from. Okay, so not too far away. It was a fairly short flight. So I'm coming from up here in the state of Mississippi to you in Sao Paulo. And if we zoom in on Mississippi, my school is located in Jackson, Mississippi, right here in the middle. We are close to the Mississippi River there, only 45 minutes drive from my school to the Mississippi River. And this is the capital city of the state. However, it's a sparsely populated state, so even the capital city is low in population. The greater Jackson area, we have only 200,000 people. So much, much smaller than Sao Paulo. Yeah. And the reason for the low population is it's mostly a farming state. That's the main industry, is farming. This is the medical center just north of downtown Jackson, and you can see all of the natural areas that we have around. So the state is largely untouched. We have lots of nice forest for hiking. We have good fishing, good hunting there, a lot of outdoor activities. And these are the friendliest group of people I'm working with now that I've ever worked with at any school before. So it's a wonderful place. And if anybody is thinking to come and do a sabbatical or to do graduate studies, please don't hesitate to contact me. And I'd be glad to share a wonderful school and environment and people with you. Okay, so what about the people we have within the biomedical material science department at my school? So now we are 5 faculty members, and we currently have 6 graduate students, and they come from both engineering background and dental background. We have a mixture. And we also take the undergraduate students currently in dental school and intending to go to dental school. And we have 9 staff members in the department providing support also. Among our faculty members, we cover many areas, specialty. I will talk a little bit about fatigue today, planning fatigue experiments. For those of you who have a study that you're beginning to plan, we'll try to talk about how to do that more efficiently. But we are also covering polymers, tissue engineering. We do a lot of orthopedics research in my department, not just dental materials. We are doing dental composites and doing some corrosion and fatigue of metals also. So we cover a broad spectrum with just 5 faculty members. Okay, so we have already heard a little bit from you and from Ulrich on these materials with cracks in them, and the cracks are growing over time due to various mechanisms. So you've already gotten the idea that usually the cracks in a material, the flaws in a material, when it's first placed in the patient's mouth, are not enough to cause failure under the loads or bite forces that they see in the clinic. So what type of loads are we seeing? We may consider this to be a worst case scenario, that a human might deliver in a single clinching event 600 newtons, 200 newtons maximum maybe for heavy mastication, heavy chewing, and probably a little bit less than that in everyday life. And what type of stresses those induce in the materials we're talking about? Well, studies have shown based on finite element modeling that in the veneer layer of all ceramic restoration, these are probably inducing stresses from 18 to 29 megapascals, depending on the angle and location of load application, as long as we're not talking about parafunction or trauma. And the core ceramic, a little bit higher stress levels. And again, finite element modeling studies have predicted for implants. In typically the weak point in the implant is the abutment connector screw, and that we will see a stress level for a standard diameter implant ranging from 100 to 200 megapascals in the connector screw, and much higher for a reduced diameter implant like we might use in the anterior of the patient. Okay, and so these stress levels are much lower than the strength of the ceramic materials. And these stress levels are lower than the yield strength, and of course lower than the ultimate tensile strength of titanium. So just considering the information we have on this slide, we would expect to never have a failure of a restoration or an implant, and obviously that doesn't happen. So something must be happening over time. When the implant is first placed, when the restoration is first placed, the bite force is not enough to cause failure to happen. Something changes over time. That's the subcritical crack growth that you and Ulrich have been talking to you about already. And so we have some equations here. However, you've had time to finish digesting your lunch, and the blood is coming up back to your brain, and it's carrying the espresso from the coffee break with it. So I think we can handle some equations in the presentation now. And I just want to give you a background before we talk about designing the fatigue study. I'll give you a background what's happening on a molecular level with the propagation of the fatigue crack. And so we have sigma is usually used to represent the stress on the material. And some people think that each material has a certain stress level or strength that material will typically break at, and you're probably realizing by now that is not actually the case. That it is not, material does not have failure stress as a material property, but rather there is another thing that defines the fracture, and that is the stress intensity factor. Material has a stress intensity factor, a critical level at which failure will occur, and the size of the cracks in the material will determine what stress level is necessary to cause the stress intensity factor to reach its critical level, which we abbreviate with K1C, and we also call that the fracture toughness. Okay? And so we have a piece of material here, and we are pulling on it with some force, and that force will induce a stress all over the material. In this simple case we have drawn here, the stress can be calculated by dividing the force by the cross-sectional area. Force divided by area is stress. However, the material is covered with lots of flaws, cracks, pores all over the surface. And if we look closely at that, we can see that the stress far away from, if this is the flaw in the surface, the stress far away from that flaw is concentrated by the presence of the flaw. So in the material near the tip of the flaw, we have a concentrated stress, and that's what I'm talking about when I say stress intensity factor. And you can calculate the stress intensity factor by multiplying the far field stress that is all over the material times the square root of A. A is the flaw size. So this is the size of the crack that's going to be growing into the material. And Y is a factor that tells us the shape of the flaw and the location of the flaw. Okay? And what happens as these cracks grow through the material over time? We may have mastication forces causing a cycling of stress, and because the stress intensity factor includes the stress, then the stress intensity factor K will also cycle up and down during chewing. And we may have a constant chewing load causing a constant cycling of stress, constant amplitude stress in the material. However, as the crack grows, A becomes larger, and so even for a constant chewing load, the stress intensity factor gains higher and higher amplitude over time, eventually leading to failure. And what we observe clinically is what statisticians call the bathtub distribution. If we look at how many of the restorations are failing on the y-axis, and this is over some period of time after placing the restoration on the x-axis, then we see that in red here, these are the restorations that are poorly designed, or they are placed wrong choice of materials for that location, or they're placed in a patient who has parafunction, and we have failure almost immediately. And those begin to fail, then the number of restorations failing decreases over time. But at the same time, these cracks are growing in the material, increasing the stress intensity factor, and the material begins to wear out, and more the restorations will fail due to the growing cracks over time. And when we add those two sources of failure together, we get this blue curve. This is the observed failure rate over time, and that's what we call the bathtub distribution. Okay, so why are these cracks growing, though? We have two mechanisms for the crack growth. One is stress corrosion, and the other is cyclic fatigue. First, let's talk about what happens in stress corrosion. Usually we think about ceramic materials when we think about stress corrosion. And ceramic materials, many of them are mostly a combination of silicon and oxygen ions. So I'm representing for you here the surface of a ceramic material as a network of silicon and oxygen ions, and there is some crack in the surface there. And there is some saliva present in the surface of the material, and so some water is coming into the crack from the saliva. And what Steve Freeman showed is that as we bend the ceramic and induce tensile stress on the outer surface, then that crack will concentrate the stress intensity factor and will eventually reach a high enough level that it passes a threshold and has enough energy to split the bonds in between the silicon and oxygen ions, and the crack grows larger. And when the crack grows larger, even under the same stress, we will get a higher stress intensity factor, so the crack will accelerate, growing faster and faster over time. And water helps out with this. So the water is coming into the tip of the crack and acts as a catalyst. The oxygen, and you know, water is a polar molecule, and the oxygen has a slightly negative charge on it. Hydrogen has slightly positive charge. And so the negative charge on the oxygen ion in the water is attracted to the positive charge on the silicon, +4 charge, and it attaches, and positive hydrogen attaches to the negative charge on oxygen, and the water reduces the energy necessary to split the silicon and oxygen apart. So it's a catalyst for stress corrosion. And what I'm showing you here is a fracture surface from a piece of porcelain that we broke in my laboratory. And you can see on the surface the pore, the flaw that generated an initial crack and began growing slowly through the material while it was under stress. And if you look very carefully, you can see, and to help you, I've drawn some red arrows. This is outlining the size that the crack grew to before the material broke.